I know. I'll get you towards the end. I'll just make sure you're all not marked absent or late. Okay, so first up, I have up there on, yeah, that breeze is cold, huh? Wow, we are really sparse today. That's okay. I have got tons of reviews up here for you. Several that we did from 2019, and then I've got the review key for ours up here. This is not a voiceover, it's just a PDF of all the answers. Okay, so all the answers are up there. Okay, I will record what we're doing today, and I'll put that up there too, so you can go back over as I'm writing down problems and doing them. You can see how they go. But I did put a key up there for you that looks. Let me see if I can bring this up real quick. There it is. It looks sort of like this. I took a picture. I don't want to take a picture. It has color on there, so hopefully you can follow through on the color where things are. But I will go through it with you, the problems that you want to. At the end of your packet, there was one problem that we did not do, I think. If I remember right, let me see if I can find a packet real quick. I think I'm out of them, but if you got your packet from the okay, at the very end, before the multiple choice was there, yes. Okay, I want to go through this one really quickly with you because we did not do it. I don't think we did the last couple, if I'm right. Did we do this? Yeah, I'll get you in a minute. I haven't got into it. Did we do this one at the bottom here? Did we finish this? Okay, so I want to just really quickly go over where did we finish? So we were right here. Okay, let's go over this really fast. I'm just going to extend this out, see if I can get this to. It's not going to let me. All right, well, we'll try and make it as big as I can for you. All right, so classify each of the following as endo or exothermic. This should be very fast. I'm going to finish the last of the notes really quickly because there's some of it that's like the test, and then we'll go to the review. Okay, so really quickly, you should be able to say if it's giving off heat, it's exothermic. If it's taking in heat, it's endothermic. So right here, condensation, exothermic. Boiling, endothermic. Sublimation, endothermic, because you're putting heat in for it to go from a solid to a gas. Liquefaction. Liquefaction, you're taking a gas to a liquid, so it's exothermic. Freezing, exothermic. Vaporization, endothermic. Okay, then we get down to evaporation and vapor pressure. So when we look at evaporation and vapor pressure, you want to look at how many particles are above the liquid, or if there's any liquid left. Okay? So evaporation is just that, the liquid going into the gas. If it's in a closed container like this one, we get what's called vapor pressure. That's these molecules hitting the sides above the liquid. Okay? The evaporating molecules carry away from the liquid energy or heat. So as they evaporate, it becomes cooler. That's why our body sweats, so that it can cool that down, because as that sweat evaporates, our bodies are cooled. Okay, the remaining liquid in here becomes cooler. What's the process above called? It's called evaporation. If it's in a closed area, it's vapor pressure. Condensation is when those particles become back to liquid. And vapor pressure, again, is that pressure that is formed by those gas molecules above a liquid in a closed container. What types of molecules tend to have higher vapor pressures, polar and nonpolar? What do you think?
Nonpolar.
Higher vapor pressures will be polar because they'll be attracted to each other. Okay, now here was a sort of a thing looking forward, back and forth. You've got two things that you put on your back of your hand. Which is going to evaporate first? You've got ethyl ether and methyl ether. So ethyl ether has two carbons on each side of an oxygen. Methyl ethyl ether has one carbon on one side of the oxygen, two carbons on the other side. So if you look at it, this has less carbons than this has less hydrogens than this, and this has the same amount of oxygens. So the smaller molecule, the smaller weighted molecule is going to evaporate quickly. Sublimation we already talked about. It's going from a solid to a gas. Melting point is when you go from a solid to a liquid. Decomposition is when you're falling apart. And what are three common substances that sublime? What are they? You should know them. We talked about one of them. One you guys like to play with. Dry ice. CO2. Okay, another one is iodine. And a third one, those are the ones that are most common. I have to think about the third one for a minute. Camphor. Camphor does that. So camphor is the smell that Vicks has. Okay, so that's camphor. Camphor sublimes. Okay, so here we come back down to this. This is where I wanted to get, because we didn't do a lot of these problems, so I want to make sure we do this. So these all have to do with the Q equals MC delta T. And you'll see me write CP sometimes instead of C. C is just a specific heat. So here it said CP, we're going to put CP. Here is your mass. This is going to be your change in temperature. Change in temperature is the final temperature minus the initial temperature. Okay, and then you got CP, so plugging in. Q is equal to the mass, 210 grams, times specific heat, which is 0.39 joules per gram degrees Celsius, times by the change in temperature from 95 to 40 degrees Celsius. So plugging that in, grams go out, degrees Celsius go out. I like to do the 95 minus 40 first, just so it gets out of the way. Except this is a dead calculator, so that's not going to help me. Parker, you with us today?
Yeah.
You got this you got this packet? Probably ought to get it out.
So I got 4,504.5.
4504.5 is calculator throw up. That's joules. How many should I report? Good, 2. So what should I report?
4.
Yep, you could do that.
Wait, what?
Awesome. So moving it 1, 2, 3, and I only want to really report 2.
So why wouldn't you just do 4,500?
If it's bigger than 1,000 or less than 1,000, that should go into scientific notation. I know. Okay, let's flip over the page, because there's a couple more that we want to try at the top here. And then I want to do one like the bottom. So here we have steam going from, again, here's my mass. Here's my change in temperature. And here's CP. So plugging everything in, Q equals mass, 500.0 grams times specific heat times change in temperature, 150 minus 110 degrees Celsius. Again, degrees Celsius will go out, grams will go out. Okay, and we end up with, throwing that through the calculator, 40 times 2 times 500, 4.0, because we have 2 significant figures, times 10 to the 4th joules. Okay, same thing here. Going through, we would Q is equal to 150.0 grams times 0.14 joules per gram degrees Celsius times 300 minus 120 degrees Celsius. And we end up with grams going out, degree C going out. .8 times 10 to the, did I do that right? Times 10 to the third joules, is that right? Is that what you guys got? 150 times 0.14 times. Yeah. Okay. Now, there's going to be a couple of problems on there that aren't just set like that aren't just as nice and pretty as that. One more like this. And I broke this one down into steps for you, but she won't have it into steps. Let me come back out a little bit. So she'll have just giving you the top part right here. So the thing that you need to do is look at this and say, okay, I'm going from a negative 130 or negative 30 to 130. So I know that water melts at 0 degrees, right? I know that it boils at 100 degrees. So I know I'm going to have to come from this negative 30 down here, clear up above where steam, I'm actually heating the steam to 130 degrees. So because of that, this heating curve, I'm going to have to do this as Q1, Q2, Q3, Q4, and Q5. I'm going to have 5 things I'm going to have to add together. Okay, this is where it gets a little bit tricky. On the flats, we don't have any temperature change. Okay, so on the flat here, we're using delta heat of fusion. On the flat here, we're using delta heat of vaporization. Okay, so take it one step at a time. I can only go as far as that area is before it changes slope. So anytime it has a slope that's not 0, I'm going to be using Q equals mCp delta T. Anytime it's flat, I'm just going to take the delta H and times it by the mass. Okay, so let's take the first step here. Going from negative 30 to 0. Delta T is 30. Okay, degrees Celsius. So I go ahead and throw in what I've just done. They gave me 60 grams of ice.
Wait, isn't it negative 30?
So to get this, delta T would be 0 minus a minus 30, which would give me a positive 30. Because it's always temperature final minus temperature initial. So this is where I'm ending in going from negative 30 to 0. So 0 is where I'm ending, so I go 0 minus a minus 30. Okay, good question. Okay, so then I'm just plugging in. So mass is 60.0 grams times by Cp, which for ice is 0.151 calories per gram degree Celsius. And she will usually give you this. The one she will not give you, that you need to either memorize or put on your card, is that water liquid is 4.184 joules per gram degree Celsius, or if she gives you calories, it's 1 calorie per gram degree Celsius. Okay, so then I put 30 degrees Celsius, and I times that through. Grams will cancel, degrees Celsius will cancel, I'll be left in calories. So 60, okay, what is it?
918?
918?
918.
918. Now for this part, I don't change, I just put down whatever my calculator gives me, because we're going to add this all up at the end. So now I go to the next step here. The next step is changing ice to water at 0 degrees. So I'm going across this flat part right here, not changing temperature. If you look at the delta fusion right there, that'll tell you what to do. So all I have to do for the Q here is just take the fusion, which is calories divided by grams, and times it by my 60 grams. Grams will cancel, and I get what? 480 or 4,800 calories. Okay, so I'm just going to put these out here so I know what I'm adding up as I go. 4800 calories. I'm just putting it on the very far end. Okay, now the next one, I'm going to heat coming up here, going from 0 degrees to 100. So 0 degrees to 100. This is, notice here, the CP we're using is 1 calorie. So from calories, we're using this. For in joules, we'd use 4.184. Okay, so Q is equal to 60.0 grams again times the CP times the change in temperature, which is 100. Good. Plugging through.
So it's just 16,000. 6,000. Yeah, 6,000.
Yep, 6,000 calories. Let me put 6,000 calories over here in my adding column. Next one, we're actually going to go across and we're taking water and changing it into steam. So we're not changing temperature, just water into steam. So I'm just going to do the Q for that is just 540 calories per gram times 60 grams. I dropped the 0.0, sorry. So 540 times 60.
Where'd you get the 60?
Clear back up here, the grams.
Oh,
You still are using the same grams all the way through. So 32400 calories. I'm going to put that in my add up column over here. And then the last step is heating the steam up to 130. So I'm going back to the Q equals mCp delta T again. Delta T is 30. Mass is still 60. The CP for steam is 0.48 calories per gram degrees Celsius. And my change of temperature was 30 degrees. So plugging that through.
What was the CP of steam again? Sorry.
It's right here. It's given.
Oh.
She would actually list all the CPs and the delta H's right underneath the problem. She wouldn't tell you when to use them.
864.
864. Good. And that's calories. Now, to get the final answer, I add this whole column up. So go ahead and add it up. Okay, I got 44982 calories. Is that what you got? Do I have a second on that, somebody?
What you got?
Okay, so I wanted to make sure we do it. This is as many possible steps as possible that you could have. She might take you on this from here to here. She might just take you from here to here and give you 2 steps, or from here to here. So you just need to know where you are on this chart and how many you'll have to do. But just add them up at the end.
What was the CP we need to know that was like 0.481?
That is water as a liquid. So water as a liquid, the CP is 4.184 joules per gram degrees Celsius. It's also 1.00 calories per gram degrees Celsius.
So 4.184 grams.
Now here's another thing I would sort of give you as a little help. If for some reason she doesn't give you a delta H or a CP you need, go through a couple more problems that might be there. Does that make sense? So don't give up if you don't have it on your card or you think you need something. Just go a few more problems and it'll be there.
That's joules
Okay?
on top,
Because I
right?
think what she did is she's taken an old test and had several things underneath and she didn't take to each of them. Does that make sense? Okay, so now off to the key, the review. Where do you want to go? What ones have you had problems with that you need to hear, get some extra help with? What would you like to do?
Can we go to the ones like 15 and 16?
15 and 16 have been asked for. Okay. These are not showing up real great on mine, but that's all right. We'll try and make them work here. Okay. The thing that you need to remember with hydrogen bonding, Okay, it has to be nitrogen, oxygen, or fluorine directly connected to a hydrogen. If it isn't directly connected to a hydrogen, it is not hydrogen bonding. So here I've got an H and an O, but that H is not directly connected to the O, so this one is not hydrogen bonding. This one has an O directly connected to an H, so this one is hydrogen bonding. And the next one doesn't even have a hydrogen or nitrogen oxygen, so that one is a no. Next one down we do have right here, so this one is. This one is a nitrogen connected to several hydrogens, so this one is a yes. This one is a hydrogen connected to an iodine, it's a no. This one is a carbon connected to hydrogen, hydrogen, and fluorines. So this is a no because the fluorines aren't directly connected to the hydrogen. Okay? On the next one, LDFs are every single one. So I could just basically go, yep, all of them. LDFs will be in every single compound. Okay, they're the London fog. They cover us all. Okay, what else do we want to look at? 5, you bet. Okay, on number 5, what we're looking at here is gas loss. So let's decide what we've got. We've got this right here, which is a volume. So I'm going to bring it down as a volume. And then I've got a temperature. So I'm going to tie those two together by putting ones next to them because it says they're the same. And it's in degrees Celsius, and I like to right away change it to Kelvin because I know it's a gas law and I know I have to be in Kelvin. So I'm going to change it real fast. And then it says it's cooled to, so here's my second temperature. Again, I like to change it right then because I know I have to have it in Kelvin. So what is that? 284.15 Kelvin. What is the new volume? So I'm looking for volume 2. Anybody know what law? What's missing? Volume 2. So I'm missing what's being held constant. So if I remember PTV, which one's being held constant? Whoops, sorry. PTV, which one's being held constant?
Pressure.
Pressure. So if pressure is being held constant, what's happening to temperature? Going from 1 to 2. Going down. So I should have a volume that goes down, right? So that's my really quick check to make sure. Anybody remember what pressure was whose law? If I held pressure constant. Charles' law. If I remember right, it's P1 V1 divided by T1. Well, I don't have P, so it's V1 divided by T1 equals V2 divided by T2. And if I don't remember these, I can go ahead and write them down on my card and say, okay, which one's missing pressure? And that's the one I use, right? Okay, so I am looking for volume 2. So I'm going to rearrange that and say volume 2 is equal to volume 1 times temperature 2 divided by temperature 1. Again, if you want to plug in before you rearrange, I don't care. Doesn't matter.
Couldn't we also say that moles are constant?
Yeah, moles are mostly held constant, so I don't really worry about them except for Avogadro's law. So, okay, so we're plugging in volume 1, 0.500 liters times T2, 284.15 Kelvin, divided by 298.15 Kelvin. Plugging in, I should end up with 0.477 liters, which compared to my beginning is less, which is what we predicted. So I'm good. Okay? Any others you'd like to go over?
Can we discuss 17?
17, you bet. Okay, on 17, what we're looking at is we want to color in blue the things that are endothermic. Endothermic means I'm putting in heat. So So to be endothermic, I'm putting in heat. So what thing is putting in heat? Melting. Okay, melting's putting in heat, so I'm going to color that blue. What else? Sublimation. Yeah, I'm going from a solid to a gas. I better be putting in heat. And vaporization. Good. Done. So she might not look at it like this. She might not have it like this. She might just write the things down. But if you just draw yourself solid, liquid, gas, and say, okay, this to this, to this, to this. Or is it this to this, or this?
Did,
Can you slide it over a bit?
when is the next review for our test?
The next review is, I'm going to have a formal review Tuesday after school, if you'd like to come Tuesday after school, or Wednesday during tutorial. Or if you want to come tonight, you're more than welcome. I don't know what the weather's going to be like, and I hate to keep you here and have it turn to ice. Okay? All right, any others you'd like to go over?
Yes, 25.
25. Okay. This one you sort of have to just know. The ones that like to do network solids,
Shutting down.
No, Miss Hunt.
the ones that like to do network solids are carbon and silicon. So if you remember that, carbon and silicon like to do network solids, then you can cross out everything else. So here's silicon with oxygen. That's sand. It is a network solid. That's a sugar. That's a liquid. That's ionic. That's ionic. That's ionic. Oh, here's silicon with carbon. That's silicon carbide they use in airplanes. Yeah.
Why is the second one not it?
Why isn't this one?
Yeah.
Because it's a sugar. A network solid will interact with each other.
How are we supposed to know if it's sugar?
Anything you have carbon, hydrogen, oxygen, it's going to be some kind of sugar, usually. Okay? The thing you want to remember with network is carbon and silicon. Now, carbon dioxide is not a network solid.
So it's CO2.
Yeah. You should know that. It doesn't combine, it doesn't attract any other CO2s. But these actually interweave each other.
Can we go over 24 then? So we're already right there.
Yep. A molecular solid is just another way to say covalently bound. Okay, so if it's covalently bound, it's going to be close on the periodic table. Those are things that you need to remember. So, is sodium and chloride close? No. Is CO2 close? Yes. Is mercury? Well, mercury is just one thing, right? No. Another thing, they have to be both nonmetals. Okay, so that helps you too. So magnesium oxide, no. Water, yeah. Okay, because remember hydrogen slides over and is like it's next to helium.
So then chlorine's not.
So that one does. Fluorine's no, because it's not a solid. It's asking for a solid anyway. And we can make CO2 a solid, but fluorine doesn't like to be a solid at all. NH4, Cl. No. Bromine. No. Argon.
No.
And methane. Actually, methane is sort of, it's iffy. I'm just going to put iffy.
What about for the purpose of the test?
For the purpose of the test, I probably would put it down.
You
Sorry.
would.
Could
Yeah,
you,
but, well, if she said solid, though, I would probably, that would be hard because methane is really hard to get solid. We have found it frozen underneath the polar ice caps, so it technically could be, but it's not real pretty.
Okay, but
So if it was a question like that and you did put it down, would you get points for what you got right, or would you like an all or nothing question?
It's a partial,
Okay.
okay? All right, any others you'd like to do? Number one, you bet. Coming back to number one, the patient's blood pressure is measured at this. What is it in atmosphere? So you're going to take the 117 millimeters mercury. Now, remember my caution. This is something that you could use with your side tools. However, you need to know how to take it in and out of scientific notation. Because if you don't look at the E whatever, you're going to screw it up because she'll have it there without the E whatever. Okay? So you can also just do a quick conversion if you've written down all the things that they're equal to. So I know there's 760 millimeters mercury is equal to 1 atmosphere. I put it like that so I can cross out millimeters mercury. I take 117, divide it by 760, and I've got my answer, which is,
1, 2, 3, 4.
I got this.
Yeah, I'm sorry. Yes.
I put it in.
It's all right. Okay, any others you'd like to go over? I'm just going with people asking. All the answers, like I said, are up there. Yes, ma'am.
Number 13.
Number 13.
Hey,
It's all right. Okay, so this is asking which is the lowest boiling point. So first thing we want to look for is NOF, directly connected to hydrogen, because that's going to make it higher boiling points. So anything that has hydrogen directly connected to an oxygen, fluorine, or nitrogen, we're going to cross out because it wants the lowest. Okay, so this one has an oxygen connected, so I'm not going to count it. This one doesn't. The oxygen's in the center. It's not directly connected, so I'll leave that for the minute. This one has an OH, so I'm not going to count it. So I have two that I'm going backwards and forwards to. Now, what do we know about bigger molecules? They have higher boiling point because it's more mass. I got to get moving, right? Well, the difference between this one and this one is that oxygen. And an oxygen weighs about 16 pounds or 16 grams, right? So this one is going to be my lowest boiling point.
But then also because the other one's a diploid.
This one is, yeah, you could, it
It's a
could be a
minor.
little bit of a dipole, but not very big. But yeah. Okay. Next one that you'd like to see. This next one, by the way, is sort of hard to see right here. It actually has, there's no liquid down at the bottom. It just has dots all the way around in there, like that.
Oh, I see.
Yeah, 22, 14.
yeah, just like.
Okay, so on this one it says, consider the liquid shown in closed containers, which has a higher vapor pressure. Higher vapor pressure means I've got more gases that are hitting the walls, right?
I can see it.
So that one has the highest vapor pressure. I got the most things hitting the wall. This one would have the lowest. So if she asks about the lowest, that would be the lowest. Because there's no gas above the liquid.
Which ones?
This one. Because there's no gas above the liquid. This is the highest. Okay, any others? Yes,
Number 18.
number 18. Don't be shy if you want one done. Okay, so this one, what volume, so I'm looking for volume, does this many molecules of oxygen at STP? Okay, this is a very important thing, STP here. Because at STP, I know 1 mole is equal to 22.4 liters of any substance. Of any substance. So then I don't have to use the gas laws. I can just do a conversion. So I start with what I'm given, 4.56 times 10 to the, what is that, 28? 26? Sorry, I don't have my glasses on. I should probably get them on. Molecules of O2. And I set up my factor label. I put 1 mole of O2 on the top. I put Avogadro's number on the bottom. That way, molecules of O2 will cancel out. And then I put 1 mole of O2 on the bottom and 22.4 liters on the top. Moles cancel out. Make sure when you put it in your calculator, you put that whole thing in the bottom in parentheses. And we should end up with what? See what you get.
Miss Howell,
Yes.
this calculation.
Oh, it's stuck on go exit on that screen stuff. It should be far right.
It's something we do.
You just have to hold it longer. It's being dumped there. When it's in that mode, you have to hold long. Okay, we should end up with 1.70 times 10 to the 4th liters of oxygen. Is that what we got? I did this late at night, so I'm hoping I did my calculations right. If not, let me know and I'll fix it.
What did you get?
That's what I.
Uh-huh. This calculator doesn't have Avogadro's numbers saved in it.
I got like ease or thickness.
So you did not put the bottom in parentheses.
No, because
Because this right here, 26 and 23 would be about 50. So that's how I know. So you need to put the whole thing on the bottom in parentheses. And a check for that is this is 26 minus 23. Basically, that's how you do the thing. So you should be 3 up here at least. And this is less than that, so it'll move it.
Oh, so it's 16.
Right. The calculator answer was 69661.0871, blah, blah, blah. That's calculator throw up. We need to make sure we change the calculator throw up into the correct sig figs and report this. Okay? All right. 45, you bet. Okay, on number 45, you're looking at heptane. And heptane, you want to look at the forces. Remember that the forces are LDF, they're dipole-dipole, and they're hydrogen. So we know everything has LDF, so that's a check. We're looking for what kind of things it has to overcome. I'm now looking for a dipole. Is there a way that there's a positive and negative side to this molecule?
No, it's even.
No. And are there any nitrogen, oxygen, or fluorine directly connected to a hydrogen?
No, so it's just LDF.
So it's just LDF.
I mean, this question is worded.
Yeah, you sort of got to look at it because I purposely worded it the exact same way she's going to word it. So make sure you're understanding what the question's asking.
I mean, it's going to be a multiple choice. So
That is going to be multiple choice, but just watch.
can you go over the 49 through the true or false?
The 47 through 50, is that what you're looking at? Okay, so 47 through 50. We'll get to this. So on this first one, it's a little bit tricky, the way that she worded it. And you've got to be careful, okay? On this first one, she's saying, if I have this many grams of this and this many grams of that, and they're putting to that container, are the partial pressure of N2 will be less than the partial pressure of Ne. Well, it's all about mole fraction. So first of all, I have to change these to moles. So I'm going to take the 110 grams of neon, and I'm going to change it to moles. So 1 mole of neon, there is 20.18 grams of neon. And I'm going to end up with 5.45 moles of neon.
Wait, how do we know that?
I'm just changing it to moles. Okay, because I can't compare them unless they're moles, remember? So I have to go to moles no matter what. So on the other one, I'm going to take 110.0 grams of N2, and I'm going to convert that to moles of N2. I'm going to have to take 2 times nitrogen, which is 28.02. And guys, I am really sorry about the one that's online that I gave you for the thing, because I had my computer is not playing well with me, the touch screen, and so it wouldn't go with the pen, so I had to use my finger, and it's not real pretty. I tried to make it as best I could, but it's not pretty. So just use your powers of discernment when you're looking at it. Okay, and here we get 3.93 moles of N2.
That's true.
So if I look at this, it's a mole fraction. There's more moles of this. Because there's more moles of this, it's going to hit the wall more. So the partial pressure of this is going to be higher than the partial pressure of this. Well, it says the partial pressure of N2 will be less than Ne, and that's true. So this one is true. But you have to change it to moles. It looks like they're the same. If she said molecules and molecules, they'd be the same. Because she did grams and grams. Does that make sense? So watch that. Okay, next one. 2 molecules of diethyl ether that has this structure are capable of hydrogen bonding with each other. What do they have to be hydrogen bonding? Nitrogen, oxygen, or fluorine directly connected to a hydrogen. Does this have that? No. So because of that, it's false. Energy is taken in when less organized state is converted to a more organized state. Well, wait a minute. Less organized would be like gas going to a liquid. Energy is taken in when I do that. Is that true?
Oh, it's taken out.
No, it's taken off, so this is false. Now, if I was going backwards from a more organized state to a less organized state, that would have been true. Okay, so just watch what she's talking to you about. Draw it out if you have to. Make a picture. Okay, KCl has a higher melting point than glucose. What do I need to look at here? Okay, so molecule size, so I've got one that's about 39 and 35 versus 6 times 12 plus 12 plus 6 times 16. But that's not all. What else do I need to worry about? That's the hard way. What's the difference between these two compounds? Where are they on the periodic table? This is opposite sides of the periodic table, right? That's ionically bound. What do I know about ionic compounds? High melting point. Okay, what's this right here? This is covalent. What do we know about covalent molecules? Low melting point. So, KCl has a higher melting point than glucose. True. Okay. What other ones would you like to go through?
How much more time do we have left?
It's on the board. 1:15. We've got 15 minutes.
Can we go over the six?
26. Okay, on 26, we're just basically looking at the graph. It didn't show very well, but this is a cooling graph, which is the opposite of the heating graph. Okay, so basically label freezing, condensing, cooling, cooling the gas, cooling the solid. So here, right here, I'm cooling the gas. Right here, I am condensing because I'm changing states. I'm going from a gas to a liquid. Right here, I'm cooling a liquid. Right here, I'm freezing a solid. And then right here, I'm cooling a solid. Okay, so the flat points are the points at where my boiling point and my freezing point are, or my boiling and melting point, or my condensation and melting point. They could call them all those things. So this condensation right here, condensing, that's my boiling point, which is 85 degrees Celsius. Right here, my freezing point is 10 degrees. It could also be my melting point, depending on what direction I'm going. Now, having that said that, you've got another one on the next page that I screwed up on, so I'm going to point it out real quick. This should have been heating a liquid, heating a gas, and heating a solid. I did a copy and paste and forgot to change those. Okay, because this is a heating curve, so it's going the other way. We're growing and getting hotter. Okay? But the same thing's going to happen at each of these things. This one doesn't hit right on a number, so you're going to be between. I'd probably say boiling point here is about 78 degrees. Freezing point, 40. Okay? What's this?
Heating of the solid.
Heating a solid. What's this flat point? Melting, yep. What's this point right here? Heating a liquid. Yep. Or boiling, either one would work. And I probably should have had that up here. It should be melting and boiling. Sorry, I didn't change that. And then this is heating a gas. And just remember, at any time there is a slope, I'm going to use the equation Q equals MC P delta T. Anytime I'm on a flat, I'm just going to be using delta H vap times the mass, or delta H, actually that one is fusion, sorry. Fusion and vap times the mass to get Q. Okay? Any other questions? I'd like to go over. We got 10 more minutes.
Wait, what is that? C2? CP?
Which ones? MCP delta T?
$29.
29. Okay, how much energy does melting this much of solid water require? This is one of the ones I told you might have to look at another point because she just mixed them up, but she didn't put the stuff with them. So find really quickly, we need delta H of fusion for ice. So I would look at the other problems and say, or write it down. Here's the heat of fusion of ice right here on this one. 334 joules. So 334 joules per gram. And then all I have to do is just take that and times it by the mass. Grams go out. And I've got this up there wrong because I did the heat of fusion in kilojoules. I think she, let me see if it does the same. Yeah, it ends up the same. So 684,700 is the joules I got. If you divide it by 1,000 to get it into kilojoules, it's 684. Basically 685 kilojoules. I happen to know, and I was at home, I didn't catch this till later. I used the heat of fusion of ice is 6.01 kilojoules per mole just because I knew that. So I changed this to moles and then I went through.
Can you move the paper over a little bit?
Okay, that's not supposed to be a decimal there. Okay, any others that you'd like to go over?
What are the harder ones in the calculation?
It just depends on what's hard to you.
What requires the most work?
Well, those ones that we did that we had to go through each of them, like these ones right here. They're not hard, but they just take a lot of time. So she will give it to you like this instead of saying this is step 1, step 2. So you've got to picture it first. You want to do one of those?
Can we do one of those?
Okay, so the first thing that you want to do when you come to a problem like this, I'm doing 34, is you say, okay, I've got this much mass. That's going to be my mass throughout. And I'm going from ice to steam. So if I look at this, I know I'm going to start right here on this flat, 0 as ice. It's going to go up, and it's going to go to 100 as liquid, but then I want to get to 100 as steam. So I'm going to go through 2 flat areas and 1 long area. So I'm going to have 3 Qs. I'm going to have Q1, Q2, and Q3. Okay, I'm going to zoom in for a little bit right here. So I'm going to have 3 areas that I'm going through. So the first one is a flat area. So on Q1, I'm going to take heat of fusion times my mass. On Q2, I'm going to go mass times the specific heat of water times the change in temperature because I've got a slope. On Q3, I'm back to a flat area, but this is delta H of vaporization times my mass. So now I just plug in what I have. So delta heat of fusion right here is 334 joules per gram times by my 75 grams. I'm just setting it up. I'll do the calculations in a minute. This one right here, I've got the mass of 75 grams. The CP for water, I'm looking for water because they gave me a lot of different things here. CP for water is the 4.18. They just did the 4.18, so that's what I'm going to use. Joules per gram degrees Celsius. And the distance is from 0 to 100, so the change in temperature here is 100 degrees. And I'm going to plug that through. And then the last one here is heat of vaporization. They gave us that right here, 2,260 joules per gram times the 75 grams. Now, I'm going to plug those all through. I'm going to get answers for all of that. Then I'm going to add them together to get my total amount. So plugging through. I got 25050 joules to melt the ice. I got 31,380 joules to heat the water. And then I got 169,500 joules to boil to steam. And adding those all up, I end up with 225,930 joules. That's my total. Okay, so each part isn't hard, it's just a matter of making sure you've got each of the parts. And I think the big thing that has helped me with these kind of problems is visualizing where I am on that heat curve or cooling curve and what steps I need to go through at each point. If I've got a slope, it's Q equals MCP delta T. If I'm flat, it's just heat of vaporization or heat of fusion, depending on where I'm at, times the mass. So not hard, you just got to remember the steps.
I got a different number for like that
For adding them all up, or which one?
for Q2.
For Q2, let me put it through again.
That's what I got too.
And 50 here, yep. It's probably because I put the 4 in, 4.184, because I'm so used to it. So that's gonna take this down by, what was I before?
Just right there.
So to a 0 there.
Then what would be the sig fig for that?
So that's where it becomes hard. At this point, I just keep this and I look at her closest answer. Because if you take this through a sig figs, it's 2 here, so you drop these. Take this through, it's 2 here, you take these 2,
So
take
that's
these 2.
what inside
And then when you add it, it's different because it goes to the least they have in common. So it gets really hairy. I haven't noticed that she's really stickler on this one as far as sig figs, because there's too many rules for this one. So just keep them, add them up, and find the closest. Okay? Do you want to do another one like this? We got about 3 minutes left, or you want to leave the other 2 to try on your own?
So then tomorrow,
Yep, after school tomorrow, and then Wednesday, right before the test, I'll have that period open. Okay? So are there any last minute questions? Got about 2 minutes, 3 minutes left. I'll put this one up so you can see it. So you see us working through it. Is there any others that you'd like to look through? Carrie? No. Sam. I need to talk to Kara because she's not on my roll.
She said she withdrew from the class.
She withdrew from the class. She didn't withdraw from Weaver.
I saw her the other day at school and she said that she dropped the class, so.
But she didn't drop from Weaver. She's still on my Weaver rolls. So she's going to end up with an F.
If I find her school again, I'll talk to her about it.
Okay.
don't you have to drop the class?
Yeah.
So no
But
matter what, you get that.
Well, typically,
she'll get a W.
a lot of colleges see the W on your transcripts is worse than an F too.
Yeah.
As dropping the class?
Yeah. Instead of getting an F just for failing, they think withdrawing you gave up, and so they don't
Water.
Because even
take a chance on it.
like don't do well,
You, at least you tried and stuck it through. That's what they're looking at.
That's what I did. Not gonna lie. I didn't want to drop the class. Now I'm having a B plus. Satisfactory.
Yeah. And you can keep pushing and get up higher.
So how much is the test at the end of the year?
20%.
Wow.
So you still want to hear after school today then?
I'm gonna be here. I don't want you guys to get stuck here with.
Yeah.
So I'll be here if you need me, but yes.
So like this last week I wasn't here and we had like the other stuff. So I was in work every day this week. Because I have my but I was wondering if next week I can still have we can try to get him. Because I was there the first time, I did the first one, so I had the first one shot, but I didn't think of the rest. Yeah, it didn't sound like it was, but it was more of just wanted to talk to you about it, figure out okay. And the learn splits and homework and stuff are still over, right? Okay, because it just said that you put in the over it, but when I checked it said it was still open. So I
They're
was
still
trying to-
open actually till May,
Yeah, that's what
but I have to have a grade. So
but I can still do
you
it.
still do.
I was gonna get them done this week.
Okay. Guys, make sure you get your Learn Smarts and your homework done before the test. They really do help you on the test. Okay? To have the information. If you need a 3x5 card, there's several over there. You're more than welcome to take some and get them done. Please get your labs in too. That's killing some of you because you don't have labs in.
When are like the labs cut off?
So May, but for your grade for third term, 17th of March.